Welcome to note set number 29, where we'll be talking about FIR filters, or what some people call FIR filters. And if you remember, FIR filters are the same thing as non-recursive filters. So what we're going to do here is look at three different methods for designing FIR filters. You'll also recall that we said that FIR filters have only poles at the origin, so they're guaranteed to always be stable. We didn't state this before, but all the design methods that we will look at are able to achieve perfect linear phase designs, and that's a good thing. We've said that that's one half of the ideal filter requirement. So it's good to be able to maintain that. In fact, that's one of the reasons for FIR non-recursive filters to be one of the most widely used discrete time filters, because of the key reason is this linear phase response. So that's a big part of this. Now, the only downside of FIR filters is that they can be computationally complex. We have to do all these multiplies, and we have to do all these additions. So to get good quality filters, we may need something on the order of 100 of these or more, and so that could end up requiring an awful lot of multiplies and additions. Now remember, this may not be the only thing that you're doing on your computer, or you're trying to fit this onto as tiny a processor as possible, and put this into a tiny little thing that will fit on the head of a pin, perhaps, in an extreme case. So you shouldn't be thinking, well, my laptop can do lots of multiplies and additions very easily, real fast, but we're not trying to put this on a laptop necessarily. We may be trying to embed this in a hearing aid. Okay, so you should keep that in mind. So our general goal in designing these things is to meet whatever our desired specs are, but to meet that with the smallest number of coefficients here that's possible. So we've already looked at taking a sinc function and truncating it as a way to design these BM coefficients, and we saw, yeah, well, it worked, but we didn't really get the best performance. Pass band was kind of okay, but the stop band, not so good, and that was even going out to 120 elements. We could push that farther and get better filters, but the question is, if we're going to be spending 120, why not try to get the best we can for the 120 that we're spending, or vice versa. If this is a suitable, if this blue 120 value response is acceptable, maybe we can get it, if we're clever, with fewer points, and therefore be more efficient in our implementation. So those are all the things that we're trying to do. So if you remember, these values of the coefficients define the frequency response of our filter, and we can get that easily through freq z as well. But the fact that our frequency response is a DTFT of this signal, so to speak, and we see that we have these sharp edges on our signal. The DTFT is assuming, just by the nature of its mathematics, since you're not telling it that there's something outside of that range, it's effectively saying, oh, okay, it's 0 outside that range, and therefore we get these the potential of these sharp transitions. And so those discontinuities, as does any discontinuity, and any sharp change in a signal requires a large amount of high frequencies to create that. So if we think of this as a signal, and we think of this as the DTFT of it, it's no surprise that we end up getting this poor response. So it's pretty clear that it's that discontinuity that's causing our problem. So one way to attempt to do that is, or to fix that, is to take this sync function and apply a tapering window to it. This thing tapers down on each side. I'm just showing one such window, just made up shape, but there are some very special shapes that are available for doing this. But the idea is it tapers this thing down more smoothly to zero. And if we do that, we can get a better design out of this. Now, Matlab has a nice function for doing this kind of windowed sync function design, and it's called FIR1. And it also has a lot of window functions that will allow you to choose appropriate windows. So you call FIR1, you tell it what is the order of the filter that I want, value of M. You tell it what frequency you want as your cutoff. And then you tell it what window you want to use. Now the window you'll need to have a length of M plus 1, since order M ends up being M plus 1 coefficients in your B vector. And some windows have optional commands or optional parameters that you have to put in. So that normalized, that cutoff frequency is normalized between 0 and 1. 0 corresponding to 0, 1 corresponding to pi. So if you wanted 0.6 pi, you'd put in 0.6. So the specified window, we'll talk about some of the names of the possible windows that you can pick. And FIR1 has many other ways of calling it. And you can design more than just low-pass filters with it. And if you type help FIR1, you'll get lots of information about other ways to call it. So here's a few designs that I made with FIR1. I kept the order to 30, and I used a couple different windows. So RectWin is a rectangular window which really does no windowing at all. So that was our original approach, where we just truncate. It doesn't do any tapering whatsoever. The Hamming window is another popular window. Now be aware that there's another window called the Hanning window, but really technically that should be called the Han window, but sometimes it's called the Hanning window. So you can check that one out as well. And a very popular one is this ChebWin. That's a Chebyshev window. And that has an alternate parameter here that allows you to try to specify the amount of attenuation in your stop band. So I put in 60 dB in there to try to achieve a stop band attenuation of 60. So let's see, this is the green one, and you can see that the green one, here's 60, here's 80. I achieved more than 70 dB of attenuation. So just because you put in 60 doesn't mean that it gives you 60. It just helps you kind of adjust. And you can see that when I put in 100, I got almost 120. Now, another big thing that we can see here, though, is that, a general trend is that I'm fixing the value of M, so I'm sticking at M equal to 30. And when I choose a window that helps me get a lower stop band level, it rolls off slower. So my transition band increases in width, but I get better attenuation in my stop band. And that is a fundamental trade-off in all of these designs. It's very hard to get both of those. But you can get, we could make this transition band shorter or narrower if we went to a higher value of M. So the design of this is a lot of trial and error. at least using this method of FIR1. So here's another general trend. I'm fixing the window, but I'm looking at larger and larger values of M. And here we see that we can get better and better transition band, and the stop band doesn't change really that much. So with a Chebyshev 100 dB window, I'm well below my desired 100 dB, but notice that my filter rolls off much faster. So with M equal to 150, I'm getting to a pretty nice window, or a pretty nice filter there. This is a pretty awesome low pass filter. But the thing that the price I have to pay is I need 151 multiplications for every output sample. So that may require an excessive amount of computation. But these are the trade-offs that you have to do as you're doing these kinds of designs. So, as I said, this is a guided trial and error approach. So you pick a window that you think will help. You try to increase the order to get your desired transition bandwidth, and work from there. If you look at the pass bands, if you zoom in on those, you'll see that they are very flat, and so that's a good part of this design. Now, there's a second method that Matlab has available. Matlab has several methods. We're only going to look at 3 of them. So this second method is called, not surprisingly, FIR2. Now this still uses windowing, but what it does is it allows the user to specify the shape of the frequency response. Whereas FIR1, you kind of stuck with, low pass, high pass, band pass, band stop. They've got those prototypes built in. But here you can get very creative, as we'll see in an example, and it will actually try to create the filter to match whatever type of shape you're looking for. So I have a bunch of Matlab commands here. I'm not going to go through them all, but I'm going to try, line by line, but I'm going to try to give you an idea of what's going on here. So this is my trimmed down version of FIR2. So you can see I call it FIR2 min. Min meaning minimal. You really ought to use Matlab's real FIR2 command to do this, but this just shows kind of the bare minimum stuff that goes on inside it. And I've made some simplifications that aren't in the Matlab version. So like I've assumed that the order of the filter must be less than 1024. I've made some other assumptions, but some of the assumptions I've made here are actually carried over to Matlab. So like the first element of this FF vector must be 0, the last element must be 1, elements must not decrease. So you really ought to read the help commands, or the help for FIR2, to find out what you really need to do. Okay, so the basic idea is that N, you're telling what the order of the filter is, so just like we were using capital M in the previous discussion for FIR1. FF and AA are 2 vectors that allow us to specify the type of filter that we're looking for, where the pass bands are, where the stop bands are. So let's look at this example here. So my FF gives me 4 points, 0, 0.5, 0.6, and 0.1. And at 0 and 0.5, AA is giving us 1, and at 0.6 and 1, AA is specifying 0. So those 2 vectors tell us that we want to go from 0 to 0.5 with a frequency response level of 1, non-dB, and then from 0.6 to 1 we want this thing to be 0. So we're designing a low pass filter. We're striving for ideal stop band, although we won't get it. And this also is telling us that our transition band that we're trying for is between 0.5 pi and 0.6 pi. So these are all normalized frequencies. So we specify this to Matlab, and it creates this kind of function inside, and then effectively takes the inverse FFT of that thing. Now before it does that, it has to populate this thing with a bunch of points. So it'll fill in a bunch of points through here, it'll fill in a bunch of points through here, and it'll fill in a bunch of points through here. Then it'll take the inverse Fourier transform of that to try to get the resulting impulse response. Then it will truncate that thing to create the coefficients for the filter. So here is Matlab's version of populating that on a fine grid. So all of this code does all of that. Seems like an awful lot of work just to fill in some dots, but that's basically what it does. Then notice that we're specifying it only over the positive frequencies here, 0 up to 1. So we need to handle the negative frequencies, but since the FFT command, actually the IFFT command, is expecting things between 0 and 2 pi rather than minus pi and pi, we create the mirror image up here. So this is like 0 to pi and then pi to 2 pi. And then the final thing we have to do is throw in a linear phase. Now this doesn't look linear, but what's happening is I'm hitting minus pi here, and then it wraps back up to plus pi, down to minus pi, wraps back up to plus pi, because minus pi and pi are the same angle. So that's why we get that weird shape there. So what I've done is, what this code does is it specifies this for the delay or the linear phase, and then it literally does an inverse FFT on that to get the thing in the time domain. And so here's the inverse FFT of that thing, and a lot of this is just zeros, or very, very small numbers. So then we apply our window to that, whatever window we want, and we get something that looks like that. Well, actually this is pre-windowing, and then this is post-windowing. And then those are our coefficients for our FIR filter design. And so here is some things that that would be designed with that. I'm designing a low pass filter with a 0.3 pass band and a 0.31 stop band start, and I'm using my good friend Chebwin here, and so we can see that as we go up in order, we get better and better filters again, and we also see that for low orders we get this very low roll off here. Notice that just because we asked for 0.3 to 0.31 for our transition band doesn't mean we're going to get it. Notice that with m equal to 30 we don't even come close to getting that. So with this design you kind of have to look carefully to see if you're getting what it is that you have asked for. Now this is just showing one of the advantages of FIR2 over FIR1. I can create any kind of weird shaped filter. So here I'm going 0 to 0.4, and I'm showing it going from 0.1 up to 10. So from 0 to 0.4 I want my filter to go up like this. Then I want it to at 0.6 go down to a stop band, and then at 0.8 to 1 I want it to be at a level of 1. So now this is the actual design that I got out of that. I plotted it in non-dB because it's the easiest to see that it is matching my request for going from 0.01 up to 10 linearly. So it did somewhat achieve that. And I'm using a pretty high order to be able to get this wacky filter. But if we look at it plotted in dB, this is the blue filter. You can see that this straight line corresponds to this weird curve. This is because of the dB plot. It turns that straight line into a weird curve. For such a requested filter, you probably wouldn't look at it in dB. But looking at the performance of that stop band, we can see that, oh, okay, I did get a pretty nice amount of attenuation there. And then here, when I want it to be 1, bam, I'm right at 0 dB, which is the dB value of 1. Now here's another design. Here I'm asking for it to be at 1 or 0 dB, between 0 and 0.3. Then I want it to go down to 0.1, which is going to be minus 20 dB. And then I want a true stop band. So this is kind of like a two-shelf filter and then a stop band. So the lowest frequencies are not being attenuated nor giving any gain. Then things between 0.4 and say 0.7, oh, I'm looking at the wrong one. Yeah, 0.4 and 0.7, I want 20 dB of attenuation, and then from like 0.8 onward, I want as much attenuation as I can get. And this is a pretty nice filter. I don't know what the exact application of this would be, but and I need 220 coefficients, 221 coefficients to do this, but still, it's a pretty nice design. Now, one gotcha is that when the last element of AA is non-zero, so I'm trying to get some sort of high pass, and that would be the case for this filter, then the order must be specified as even, which I did specify it as even. That's just a characteristic of the math behind all of this design. And so you just can't have a filter that is like a high pass that has an odd order. So it just comes out of the math. Now the last design method that we'll talk about is called the Parks-McClellan, and this is really pretty much the optimal design method that's around today. It's called optimal equal ripple design, and we've seen this picture before. And what it does is it allows us to specify how much ripple we want, how much stop band attenuation, and where our pass band and stop band cutoffs are. Now there's an auxiliary command that's called FIRPM that allows us to tell it what we're trying to achieve, and it will give a best estimate of what the order of the filter should be. So this is a really nice design method. So these are some Matlab commands that you can mimic to design a low-pass filter with this. Now it's similar to FIR2 in that it allows us to specify what kinds of responses we want in different regions. And you do that with this FSpec and this AA. So here I'm saying it's a little different than in that than in FIR2, but here I'm saying my pass band or my first cutoff is 0.3, and up to that I want 1. Then from 0.31 on I want 0. So this is specifying a low pass filter. And if you look at the help available for this, it will explain this. And in fact, a nice command is called help desk. So if you say help desk and then FIRPM, it'll give you a lot of very precise information about how to use this in more detail. And then this is just something that you have to compute based upon your passband ripple in dB and your stop band attenuation in dB. So it creates this DEV command or quantity that you then plug into your FIRPM ord. And so when you run FIRPM ord, it gives you an estimate of the order that you'll need, but it also generates a few other things that you can use, that you can put directly into FIRPM. So you run FIRPM and you get 4 things returned, and then you put those 4 things directly into FIRPM, and it designs the filter. Now, you should still check to make sure that it is meeting your requirements. Now, I gave this some pretty stringent requirements. 75, I say 75, but I really did 60 dB. Well, I don't remember. I don't know which one of these is right or wrong, but so I'm asking for a fair amount of attenuation and a really narrow transition band. So I ended up getting a filter that had 385, an order of 385. So that's a pretty long filter. But you can see that I did use 60, not 75. But comparing this to a FIR design done with the same order, we see a couple things. The FIR design, I don't remember how I actually did it, but I get a lot more attenuation, but maybe I don't need that much attenuation, but my transition band is a lot worse. And if we zoom in on that, we'll see that the blue one, the FIRPM design, does have that ripple in the passband, and we allowed 1 dB up and 1 dB down. Now, I could make that even more stringent and go to 0.1 dB, but now I need an even longer filter. So all this filter design stuff, it's really trading off how much horsepower you can afford in your actual application and what are your requirements. Do you really need 60 dB of attenuation? Maybe you don't. So there's a lot of things that you can do, but FIRPM is a very powerful design tool, and it helps you design some really awesome FIR filters. So just to give you an idea, we've been talking about these pole zero plots. So here's a simpler FIRPM design filter, smaller order, just so that our pole zero plot doesn't look all crazy. Remember, we're going to have a 0 for every 1 0 for the order. So if our order was 384, we'd have 384 zeros on our pole zero plot. So this is a lot lower. It's an order 28, and we see that we get 28 poles at the origin. And the cool thing is to look to see what FIRPM does with the zeros. So for the most part, we're trying to design a pass band that was out to 0.5 and a stop band that starts at 0.6, transition band in between there. So this is pi over 2. So you can see that from minus pi over 2 up to pi over 2 as we go through this region on our unit circle, what is FIRPM doing? It's putting these pairs of zeros strategically placed straddling the unit circle. And that's done to precisely get your desired passband ripple. Then the next thing it does is to get your stop band, it just starts tacking the tent down with tent poles properly placed so that in between the tent poles it never pops up above what your design goal is, or at least not a lot. So FIRPM, excellent design methodology. You should try it out and see it, what you can do with it. You should get a little bit of experience with it. Thanks, and we'll see you in the next video. Bye.